Okay, so in section 4.4, we're going to continue factoring polynomials, but this time we're going to use something called the factor theorem. Just as a warm-up, it says list the factors of 18. And if I'm going to list the factors of 18, I know that 1 times 18 is 18. What else? 2 times 9, right? And 3 times 6 is 18. Right? They're all factors of 18 because 18 is divisible by all of those numbers, right? And we divide evenly. So fill in the blanks. 18 divided by 2 is 9, right? Therefore, 18 equals 2 times what? 9, right? This is important because since 2 is a factor of 18, notice that it divides evenly and our remainder is 0, right? Anytime a number is a factor, you're going to get a remainder of 0. Because we have a remainder of 0, we can rewrite our original expression as 2 times 9. Notice I'm rewriting it using the divisor and the quotient, right? 2 is what I divided by, and 9 was my answer for the division process. Okay? If 18 divided by 2 is 9, then 2 times 9 equals 18. The same thing is true for polynomial functions. If you divide by a factor like x plus 3, and you get a remainder of 0, that means that it is a factor. We're looking for remainders of 0. If it is a factor, you can rewrite your original function using the divisor and the quotient. This is going to come up later on in the notes. Okay? If we get a remainder of 0, then it is a factor, and we can use that factor to write a factored form. Divisor times quotient. We're looking for that remainder of 0. Okay, so that's really the factor theorem. It says when dividing polynomials, the examples had non-zero remainders. Suppose the remainder is 0. Okay. If the remainder is 0, you can just write that your answer is q of x. You don't have to put plus 0 over something. Okay. All right, the factor theorem. A polynomial f of x has a factor x minus k if and only if f of k equals 0. Okay, so again, we're looking for that remainder of 0. You can either find the remainder by plugging k into the function and simplifying, or you can find the remainder by putting k in the box, doing your synthetic division, and see if your remainder is 0 there. Okay, so you have 2 different ways to figure out if the remainder is 0. Either plug in the value and simplify, or use synthetic division. Okay. All right. So it says determine whether a linear binomial is a factor. Again, we can do this with synthetic division or direct substitution. So I'm going to do one of each. Part A says determine whether x minus 2 is a factor. If I'm determining if x minus 2 is a factor, what number am I plugging in for x there? What would x equal? Remember, x minus 2, we're trying to determine if that's a factor. What would x be equivalent to? If I add 2 to both sides, we have an x value of 2 that we're plugging into our function. Right? F of 2 equals 2 squared plus 2 times 2 minus 4. So what would that be? That would be 4 plus 4 minus 4, which is what? Cancels. Okay, so just leaves me with 4. I got a remainder of 4. Is x minus 2 a factor? No. We need a remainder of 0. X minus 2 is not a factor because the remainder does not equal 0. In order for it to be a factor, we need a remainder of 0. All right. Let's try a similar problem, but rather than plugging in a value this time, let's use synthetic division to get the remainder. You can use either way. I'm not going to tell you which way to use. Just tell me if it's a factor or not. Okay. Determine whether x plus 5 is a factor. So I could plug in, negative 5 into my function and simplify. That's one way to see if it's a factor. Or I can use the synthetic division. So that's what I'm going to do in this example. If I'm considering x plus 5 to be the factored form, then if I subtract 5 from both sides, negative 5 would be the solution form of that. That's what I'm going to use in my box. Then for synthetic division, I list the leading coefficients up top. So I have 3 for my x to the 4th term, 15 for my x cubed term, negative 1 for my x squared term. What do I do for x? 0. Very good. We need a 0 placeholder for the x term, and then we have 25. Okay. Break down the first. Then I multiply. 3 times negative 5 is negative 15. Add down. Multiply. 0 times negative 5 is 0. Add down. Multiply. Negative 1 times negative 5 is 5. Add down. And then 5 times negative 5 is negative 25. And I add down and get 0. Remember, this is a remainder. So is x plus 5 a factor? Here, yes, because our remainder is 0. X plus 5 is a factor of fx. Any questions on determining whether something is a factor? Either plug it in or use synthetic division. Okay, you want a remainder of 0. All right, here's my second example, example 2. It says, show that x plus 3 is a factor, and then factor f of x completely. If you're ultimately going to want a factored form of f of x, I prefer to just start with synthetic division. Okay, if you're eventually going to want a factored form, use synthetic division to show that it's a factor. Okay, so it says show that x plus 3 is a factor. What would go in my box? If x plus 3 is the factored form, what's the solution form? Minus 3. Okay. List your leading coefficients up top. 1 for x to the 4th, 3 for x cubed, 0 for x squared, minus 1 for x, and minus 3 for my constant. See how I needed a placeholder? Make sure that you put in your placeholder. Okay, bring the first down. Multiply, add. Multiply, add. Multiply, add. Multiply, you get 3, and add. Did I show that x plus 3 was a factor of the function? Yes, because I got a remainder of 0. Okay, so that checks out. It says then factor f of x completely. So if I want to factor f of x completely, this goes back to what we did in the warm-up. Remember, if you get a remainder of 0 and you verify that it is a factor, you can actually rewrite your function in the form d of x times q of x, right? I should be able to take my divisor times my quotient and get back to my original function. Okay? So my original function now, I'm going to rewrite it. What was my divisor? I was dividing by x plus 3, right? So I'm going to fill in x plus 3 for my divisor. And what was my quotient? What answer did I get after the synthetic division? So this is the remainder, this is a constant, this is x, x squared, x cubed. So my answer was 1x cubed. Do I need to write plus 0x squared? Do I need to write plus 0x? No. So minus 1. See how I can rewrite my original function in a factored form? So that's nice. Is this completely factored though? What is x cubed minus 1? Isn't that a difference of cubes, right? This right here is a difference of cubes. What's x cubed a perfect cube of? X, right? What's 1 a perfect cube of? 1. Okay, so we need to rewrite this using our difference of cubes formula. We're just continuing to factor. X plus 3 times. Remember the difference of cubes formula? We have a minus b times a squared plus ab plus b squared. That is the formula for difference of cubes. Everywhere I see an a, I'm going to replace it with x. Everywhere I see a b, I'm going to replace it with 1. So I have a minus b, or x minus 1, a squared, that would be x squared, plus ab, that would be x times 1, plus b squared, that would be 1 squared. Is that okay? And I'm just going to clean this up a little bit now. We'll have x plus 3 times x minus 1 times x squared plus x times 1 is just x. And then what's 1 squared? Just 1. X plus 3 I can't factor anymore. X minus 1 I can't factor anymore. X squared plus x plus 1. I could try to guess and check factor this. But 1 times 1 is the only thing that gives me 1. Is that going to give me a middle term of 1x? No, it would give me a middle term of 2x, if anything. Okay, so I can't factor that anymore. This would be my factored form. Okay? So we're using synthetic division to get the factored form. Keep in mind, you don't necessarily have to use synthetic division to get the factored form. If I started with this, I could try to use factoring by grouping to factor this. Right, my first group here, I could factor out an x cubed. I'd be left with x plus 3. For my second grouping, I could factor out a minus 1, and I would have x plus 3. Factor out the GCF of x plus 3. My leftovers are x cubed minus 1, and then just keep going, right? You still have to factor using the difference of cubes. So, 2 ways to factor. Any questions about that? Let's try one more just like that. I'm going to go to number 11 of the student practice examples, where it says show that x minus 6 is a factor of the function x cubed minus 5x squared minus 6x. It says then factor completely. Anytime you see then factor completely, you might as well use synthetic division rather than plugging it in. Okay? I would use synthetic division. So what goes in my box? 6, right? Then I list the factors up top. 1 for x cubed, negative 5 for x squared, and negative 6 for x, right? What am I missing? Where do I need to put it? 0 on the end for the constant term. You still need a 0 placeholder for your constant term. Bring the first down, multiply, add, multiply, add, multiply, add. Okay, did I show that it's a factor? Yeah, I got a remainder of 0. Here's my remainder, there's my constant, there's my x, there's my x squared. So if you get a remainder of 0, you can write a factored form of the function. Okay. My divisor was x minus 6. Rewrite this as divisor times quotient. My divisor is x minus 6. And my quotient is x squared plus x. I'm not going to put the plus 0 on there. Okay. Is that completely factored? Can I factor x minus 6 anymore? No. What about x squared plus x? Doesn't that have a GCF? Okay, so in this case, I actually could factor out a GCF from that second set of parentheses. Both terms share an x. So if I factor out an x, what's left? We would have x plus 1 would be left inside those parentheses. Okay. And I really don't like the order of this. I'd rather see the x out front. That's typically what we see. So I rewrite this just using the x out in front. Okay, but that would be your factored form. Again, you don't necessarily need to use synthetic division in this example to get the factored form. You could have factored this without synthetic division. If you look at this original problem here, you could have started by factoring out an x. And then how do I factor x squared minus 5x minus 6? X times x is x squared, right? What would multiply to give me a negative 6? Right, 3 and 2, and they would both be negative, right, in order to get the negative 5 in the middle. See how we get the same factored form as what we, oh wait, that's not right. Why is that not right? Is negative 3 times negative 2 negative 6? No, that didn't work. Let's make this a negative 6 and a plus 1. There we go, that looks better. Still get to negative 5 in the middle, and negative 6 times 1 is a negative 6 plus 9. Okay, see how we get the same thing? So, that's the idea. I've added on 4 problems to try from this section. 2 of them are determining whether or not it's a factor. You can either do this with synthetic division or plugging in the number. And then 45 and 47 are using synthetic division to get the factored form.